Hi everyone, welcome to Everything is Relative with me, Mr. K. Today we'll be doing a crash course on the topic of medical physics for Cambridge or CAIE A-Level Physics 9702. Now this is finally a topic where in your A2 syllabus you get to apply a lot of the physics that you've learned. So you actually get to see the application of many of the topics that you've learned and things put together and the usefulness of physics. It's good to learn concepts, very important to learn concepts, and also equally as important to know where and how to apply them. And so we're going to look at purely diagnostic purposes or imaging purposes of uses of medical physics, but still quite important nonetheless. And the first one we look at is that of ultrasound. And I think everyone is sort of familiar with what ultrasound is. Now, ultrasound is simply sound waves of a certain frequency. Any frequency that's greater than the range of human hearing is technically ultrasound. So humans have a range of hearing between 20 and 20,000 hertz, or 20 hertz and 20 kilohertz. And so when we say ultrasound, we mean anything over 20 kilohertz, but on the ultrasound for imaging purposes, we're talking about approximately 10 to the power 0 or on the order of 10 to the power 1, not kilohertz, but megahertz, million hertz, very high frequency waves. And just for context, the range of human hearing, of course this depends on your physiology and your age, etc. As you get older, the range of frequencies that you can hear decreases, but for an average human, it's probably between 20 hertz and 20 kilohertz, 20 hertz and 20,000 hertz. Okay, and so the first thing we need to know, and again, this is a crash course, so we're going to break it down very simply, very rapidly as well, without going into too much of the details. Whatever extra mathematics or extra reading is required, that you'd be expected to do. But very simply, you have to explain the production of each source of waves that we are going to use, or we're going to discuss in medical physics, and you have to know how they are used to image different parts of the body. So the production of ultrasound, you look at this in your textbook and you immediately want to ignore this, you want to skip this, you want to jump this because it looks fairly complicated. But if you read the section on how ultrasound is produced a few times, you realize it's actually not that bad. So basically, what we do in an ultrasound device, which I'm not going to draw, but inside an ultrasound device, we have this very nice regular crystal. You know, crystals have a lattice structure, and we take a crystal, quartz generally, but it could be any type of crystal, and with this regular arrangement of atoms, with this regular lattice structure, there's a very neat property. And so if we have an unstressed crystal, by stress I mean applying a force on the two ends that I've drawn to compress it or to tension it, this crystal is happily neutral. No charge, nothing happens. But a weird thing happens. Because of the nature of quartz, because of the silicon atoms and the oxygen atoms, we're not going to discuss the chemistry, but what happens is if I compress the crystal, I'm going to bring the two ends of the crystal closer together. I'm going to push on the top or push at the bottom, and I'm going to compress this crystal. So now you can see this crystal is smaller in size than it was before. It's been pushed downwards, or pushed together rather. And what this does, this has an interesting effect of creating a positive line of charge at one end and a negative line of charge at the other end. And so you know that if there's a positive line of charge separated by a certain distance from a negative line of charge, we have a potential difference between the two faces of the crystal. Okay, so I've generated a potential difference. I've generated the ability for this to be used as a power source. That's what's impressive. What happens if I allow this crystal to undergo tension, if I apply a tensile force? So it's going to stretch out. And the good thing about crystals is they can. Their structure allows them to do this. And so if this were a tensioned crystal, obviously I'm not drawing the crystal structure, but just imagine that this is the same quartz or whatever it may be that you read about in your textbook. It's tensioned, it's extended, or whatever, whichever word you'd like to use, both mean roughly the same thing. Then I still have a potential difference. I also induce a charge on both ends, but now the charge is reversed. And it doesn't really matter if the charge is reversed, I still have a potential difference. So if I cycle back and forth, you can see that if I cycle back and forth between a compressed state and an extended state, I have an alternating potential difference, which means I can, if I were to connect this crystal to a circuit, I would have an alternating current, an AC current would be produced. Since I had plus at the top initially, but then I had minus at the top. And then I had minus at the bottom and plus at the bottom. And so they were alternating signs. And so if I had these two ends as a power source, then I would have a plus and minus constantly alternating. And so I produce an AC voltage. Okay. So compressing this crystal actually produces a current. And we give this crystal a very special name. We call it a piezoelectric transducer, very fancy word. A transducer is simply something that converts one thing into another thing. Anything that transduces something is converting something into something else. This is converting a stress into a potential difference, or a stress into electricity. Okay, so not the type of stress that you're undergoing currently, but same idea, I guess. The tension or the compression that the crystal is undergoing actually induces a current. And that's helpful. That's a mechanical form of energy becoming electrical energy. And so if I apply a stress, I get the crystal to vibrate. If I can apply the stress, tension and compression and tension and compression, and I can alternate this very rapidly, and I have vibrations or oscillations occurring. Okay. If I have these oscillations occurring, then from the diagram above, I have a high frequency AC voltage that is produced. Connect this to a circuit, and guess what? I have an AC current, an alternating current. And so this essentially becomes a power source. So a piezoelectric crystal, piezoelectric transducer, can become a power source. Let's turn this process the other way around now. Let's go the other way. Well, if I have a power source and I attach the power source to my piezoelectric crystal, then what happens, and if I use a high frequency AC voltage, okay, now I'm not compressing and tensioning the crystal, I'm applying a voltage, an AC voltage to the crystal. The opposite process happens. It starts to vibrate. There's vibrations, there's oscillations. We've taken electrical energy and now converted to mechanical energy. Now what happens is when the crystal vibrates at a very high frequency, it pushes against the air surrounding it. When it pushes against the air surrounding it, remember, any disturbance in air will create a sound wave. A wave is just a disturbance in a medium. These vibrations disturb the air surrounding it, and guess what? Ultrasound waves are produced. And so if we can match the frequency of the AC voltage to the natural frequency of vibration of the crystal, guess what? From the topic of oscillations, we get resonance occurring. Resonance gives us a nice high amplitude of ultrasound waves. Okay, and one of the important things with this crystal is if there's a two-way process, then a single crystal can be used to produce and detect ultrasound. That's why an ultrasound scan usually has a bit of a delay. We send out the ultrasound, a little bit of a delay, we observe what's coming back, and so we can actually tell exactly how much is coming back because we can convert any sound waves reflected back into an electrical signal. So it can produce and detect ultrasound. That's quite handy. We don't need two separate devices. One device will do both. Okay, and so now we have to talk about the use of ultrasound. So how do we use it in order to generate an image? And again, we're going to discuss this very rapidly, very briefly. It is your job to make sure that you go and understand the process thoroughly. Basically what happens is, if you've ever seen an ultrasound or have been for an ultrasound, you know that the device is placed onto the skin. And so what happens, what you can't see, is the fairly strong incident ultrasound wave passes into, we use the skin in this case, but it's any boundary. And some of the ultrasound wave is reflected, going back to the transducer, which is fine because the transducer can act as a receiver as well. And so the wave that goes into the body, the incident ultrasound wave, has an intensity I0. That's the intensity that's incident into the boundary, whatever that boundary may be. But boundaries reflect waves. And so I have a reflected wave, and that intensity is different. It's IR. And the reason it's different is because some of the wave that's incident into the skin or into the boundary is transmitted. And so this transmitted ultrasound wave has an intensity IT, T for transmitted, R for reflected, I0, well, we just call it I0 because it's a peak. And so, again, this is a boundary between different media. It could be air and skin. It could be fat and muscle, or fat and tissue, or whatever, any media in the body. And so the intensity I, or I0, is equal to the reflected intensity plus transmitted intensity. Obviously, this is a very sort of idealized situation. But how does this help us? Well, the ultrasound device sends a signal into the body. The signal passes into the body, reflects at boundaries between different structures in the body, between fat and tissue, fat and bone, tissue and muscle, whatever, and comes back. And when it does, it's also detected by the piezoelectric transducer, which can then tell us very important information. The first amount of information comes from the time. The time it takes for reflection to come back to us. So the time for the reflection to be detected by the transducer tells us the depth of the boundary, how deep the boundary is inside the body. So it can tell us exactly how far the wave has traveled, and that makes sense. If it takes longer, the wave has traveled further. If it's shorter, the wave hasn't traveled that far, and so we know how deep the wave has gone in. And again, this is all picked up by the transducer and then converted to an electrical signal by a computer, and we can make the relevant images appear. The amount, or the reflected intensity, simply the amount of reflection, if I want to be very unscientific, but the amount of reflection is simply the reflected intensity, tells us the nature of the boundary. The nature of the boundary. What type of boundary the ultrasound wave is encountering. If it's reflecting more, then it is a certain type of boundary. If it's reflecting less, then we can tell it's a different type of boundary. And putting all this information together, we can actually generate a picture. Now, how do we know exactly what type of boundary we are looking at? And why even different boundaries have different amounts of reflection? And this is where specific acoustic impedance comes in. Specific acoustic impedance, which is given the letter Z, as the symbol Z, is equal to the density of the medium rho times the speed of the wave in that medium. So whatever medium it is, if it's skin, bone, tissue, etc., rho is the density of that structure. And c, don't confuse c for the speed of light, it's actually the speed of sound in that medium. Remember, the speed of sound in air is a constant, 340, 330 meters per second. But in different media, the speed is different. And so, basically, the density of the medium gives us a good indication of the specific acoustic impedance, right? And what we know is that this equation applies for a specific medium, so it's different for different structures, but it's very similar if you were to do an ultrasound to check for a pregnancy, to look for the health of a fetus, for example. The specific acoustic impedance is very similar for the water-based jelly that you would apply to the stomach and skin. And we'll see that since they are very similar, there's not much reflection. And so the water that we apply, or the jelly rather, that's water-based, that we apply to the skin, doesn't allow a lot of the wave to be reflected. So it actually allows most of the energy to pass straight through, and none of the intensity is, well, quote-unquote, wasted, if I can say it poorly, but more of the sound wave can actually pass into the body, and so we get a stronger reflected wave. If it wasn't for the water-based jelly, the dry contact between the device and the skin actually allows for quite a bit of reflection. So the water-based jelly just makes the image much clearer. And then we learned about something called the reflection coefficient. Hugely important, because if we know the reflection coefficient for different boundaries, then we know what boundaries we are dealing with. So we give it the symbol alpha, but it's simply the amount of reflection by the amount of wave going in. Reflection intensity, or reflected intensity over incident intensity. And I think this equation may be in your formula sheets, but it's good to know what it means. And so basically what we're saying here is that the reflection coefficient, or rather the reflected intensity over the incident intensity, is Z1 minus Z2 all squared divided by Z1 plus Z2 all squared. You need not know how to derive this equation. So basically what's happening here is, if I were to draw this two-dimensionally, I have a sample. This could be my skin, my bone, my tissue, etc. In comes a nice parallel ray of ultrasound waves. Okay, so this is, and it has to be parallel as well. It can't be a divergent. We're going to assume that it's parallel. And so I have a sample, whatever the sample may be, and the incident intensity is I naught, and whatever is reflected from the sample is IR. Okay, that's the intensity that's reflected from the sample. So that's a very simplified diagram of what's happening. Okay, so what we know from this, we'll actually draw another diagram a little later on that will explain the depth. But what we figure from this is that if the reflection coefficient is high, well, seems obvious, but that means there's a high amount of reflection. And different media have different reflection coefficients. If the reflection coefficient is low, there's a low amount of reflection. Okay, that's helpful. And it's low for jelly and skin, because jelly and skin have very similar values for reflection coefficient. If the values for Z1 and Z2 are very similar, you can see that, well, Z1 minus Z2 will be simply 0, very little reflection. So if two materials have very similar acoustic impedances, there's very little reflection. But if the values for Z1 and Z2 are very different, and you can do this with some simple mathematical analysis, you'll see that the reflection coefficient is very high, close to 1, which is a high maximum amount of reflection that you can have. And so for very different acoustic impedances between media, lots of reflection happens. For similar acoustic impedances, not so much of reflection happens. Okay, so that's what the reflection coefficient can tell us. And if we can figure that out for different media, then ultrasound tells us exactly what medium or media we are looking at. Now the next thing to talk about is attenuation. Now attenuation, in at least for our context, we can simply think of as absorption. The amount of the wave, and we didn't talk about absorption, we talked about transmission and reflection. But simply, attenuation means, well, how much of the wave is actually saying goodbye as it passes through a sample. And so I'm going to redraw a very similar diagram, but now with a bit more context. So here's my sample. Whatever this may be, again, fat, muscle, tissue, we're looking at the human body. So in comes parallel ultrasound waves, and they pass through a boundary between air, or the jelly, and the skin, or the fat and the muscle, whatever it may be. They come in with an incident intensity I0, and they pass through a certain amount of sample. Let's say they move through a distance x, usually measured in centimeters or millimeters, depending on what structures you're looking at. After moving through a distance x through the medium, the new intensity, if I could cut the sample and measure the intensity at that point, I would get I. And what we find, I'm not going to prove this or do any advanced mathematics, but what I'm going to show is that if I were to plot a graph of the measured intensity I against the depth, how far the wave has passed into the material, doesn't matter what the material or the medium is, we have an exponential decay occurring, which you've seen before for capacitance, but you've seen as a relationship with time. In this case, the relationship is with distance. So the measured intensity I decays exponentially with distance, not with time, but with distance. And there's a simple relationship, which is I is equal to I naught e to the minus some constant, which we'll call mu, times x rather than t. Now, mu here, the Greek letter mu, is the linear attenuation coefficient or the linear absorption coefficient. Basically just tells you how much of the wave is being absorbed. If the linear absorption coefficient is high, if mu is high, this graph drops very rapidly. If it's not so high, then the graph drops a little bit more gradually. And so if I draw the graph, let's draw the graph for A. Okay, for A, I'm going to just sketch a graph. The constant, the linear absorption coefficient rather, for A is 1.2. Okay, and obviously that's per centimeter. Remember, it has to have units of per centimeter, since we can't have a unit in the exponent for E. And so this graph actually drops fairly rapidly and then straightens out quite rapidly as well. And so that's the intensity with distance for air. And we'll do another one for water, again, just as an example. But the linear absorption coefficient for water is much smaller. It's 0.0002. And good mathematics will tell you that this graph decays as well, but a lot more gradually. And so the linear absorption coefficient is smaller. It means the rate at which the graph drops is much less. Okay, so that's basically what this graph tells us. Okay, a little bit of mathematics there. So that wraps up that wraps up the topic of ultrasound. But we then have to go on to the topic of X-rays. Now, ultrasound waves are sound waves, and obviously X-rays are electromagnetic waves, but there are some similarities, especially with attenuation. Now, we have to again talk about how X-rays are produced. Okay, so again, I'm going to move through this like fairly rapidly. If I have a cathode, heated cathode, some filament that is heated, from your cathode ray oscilloscopes or your cathode ray televisions. You've seen these structures before somewhere in your textbook. But if I have a cathode and anode, I'm going to release electrons. And if I have my anode at the other end with some metal target on it, something very specific happens. I'm going to measure the voltage across the cathode and anode, and I notice that it's a high potential difference, a high voltage. And so the energy given to the electrons that are ejected from the cathode is quite high. And these electrons move to the right in this case. And since they have high energy, they have high speed. Okay, and then they strike the metal target. Upon striking the metal target, they decelerate. Okay, so they decelerate very rapidly. And remember, when we accelerate or decelerate electric charge, what is produced? Electromagnetic waves. And so upon striking the metal target, upon decelerating, an X-ray is produced. We know it's an X-ray because we can control the amount of energy that the electron is given. And the X-ray has an energy HF or hc over lambda, which we know from quantum physics. Now, the accelerated electrons have energy eV. We know that an electron accelerated through a potential difference of V has an energy eV. This is equal to the kinetic energy that the electron finally gains just before it slams into the metal target, and is also equal to the energy in an ideal case, which is obviously not always the case, hc over lambda, which means the wavelength of a single X-ray photon can be given by h times c, Planck's constant, times the speed of light, times the charge on the electron, times the potential difference that accelerated the electron. Okay. Now, what's important to know is that the amount of energy given to each electron varies. It's not constant. Since we have a varying of energies of electrons, we have a varying of the wavelengths and the frequencies of the X-rays produced. Common exam type problem. Explain why the produced X-rays have a variety of wavelengths and frequencies. So your explanation will require a lot more wording, but that's the reason why it happens. The energies of the electrons vary. The decelerations hence vary. And so the energies of the X-rays that are produced also vary. Okay, it's not a fixed energy for every single electron. Okay, so we can then define what we call the cutoff wavelength. And the cutoff wavelength is simply the minimum wavelength. Remember, not only one wavelength of X-rays can be produced, we can produce a variety. And so the minimum wavelength, lambda naught, like we said before, is hc over eV. This is minimum wavelength of X-rays, which means we can't produce X-rays with any lower wavelengths. Okay, and so what this means is if the energy goes up, if eV goes up, then lambda goes down, which is more energy and a shorter wavelength. Okay, so All that means is if we give the electrons more energy, then the energy of the energy of the photons produced, the X-ray photons, increases. And so we have to, or rather the wavelength of the photons decrease if the energy goes up. Okay. So how do we use X-rays? How do we use X-rays to image? Well, that's important as well. We know how X-rays are produced. We need to know how they're used as well. So basically, if I were to remember, X-rays are there to image internal parts of the body, internal structures, just like all of our diagnostic tools are. It prevents us from having to do invasive procedures, having to cut you open to have a look at what's wrong. We can literally do it without actually physically cutting someone open. So if I take an example of, could be any soft tissue, works best for soft tissue, doesn't have to be soft tissue, and we have bone. Now what happens is we use an X-ray film, which is basically like the negative from an old school camera, and if we pass X-rays into this tissue, then it turns out that X-rays pass straight through soft tissue without being absorbed, and they'll get to bone but not pass through bone. They'll be completely absorbed by bone. But again, if there isn't anything blocking their path, they will happily just pass through the softer tissues, the softer structures in the body. And so these are the incident X-rays. And so our incident X-rays then strike this photographic plate, and this X-ray film then acts as a negative and produces a bunch of shadows. For X-rays that pass straight through, we have regions that are darker. And for X-rays that are absorbed and don't pass through, those regions become white. This is why your bones appear white on an X-ray image. Remember, again, this is like a negative. And so, again, where X-rays pass all the way through, we have black. And so we can look at the structure of the bones by simply looking at the white areas in an X-ray. And the amount of blackening, the darkness, how dark the darks are basically, is what we call contrast. The degree of darkening, degree of blackening, it's hugely important because higher contrast means easier to observe the structures. Okay, so you want a good amount of contrast in your X-ray images. Again, it's not always necessary, depending on what you're trying to image. Sometimes a very simple low contrast image may be good enough to say, well, there's an issue, there's an abnormality, etc. But we don't always have to only image bone or hard or dense objects. We can even target stomach problems. I mean, if you want to look for an issue in the digestive tract, in that case, generally X-rays will pass straight through the soft tissue in the stomach and nothing really would be visible. What we do is we give a patient something called a barium meal, which is just a food that has a lot of barium in it. Barium itself absorbs X-rays, and so we get white regions where the X-rays are being absorbed by the patient if we pass the X-rays through their stomach, and we can actually see if there's any issues in the digestive tract. Okay, and then there are other places we can use X-rays, not always only for bone. Okay, so we can use it for other tissue-related issues, etc. And the one thing we know about X-rays is that they attenuate just like the ultrasound attenuated. And guess what? The attenuation follows the exact same mathematical structure. So you don't have to relearn any of the attenuation stuff for X-rays. As X-rays, as when waves pass through the body, I mean, obviously in reality it's a little bit more complicated than this, but if a very idealized scenario, we have the incident intensity going in, and with distance, this incident intensity decays. And that's with the depth into the sample. So I won't redraw the diagram, but it's exactly the same as we did for ultrasound. And so what does that mean? That means, again, the relationship I is equal to I naught e to the minus mu x. Again, mu here is the linear absorption coefficient. The unit of measurement for mu, just like above, is per meter, but we don't really measure in meters, so we measure it in per centimeters or per millimeter. Okay, so just remember that the structure is exactly the same. Whether you're doing attenuation for X-rays or ultrasound, what will change though is the value for mu. The value for mu is different for ultrasound waves than it is for X-rays. Okay, obviously different structures will deal with X-rays and ultrasound differently. And so that's how X-rays are attenuated. Next, we looked at CT scanning. So CT scanning is, I won't say new, but it is a novel idea, novel concept. And CT stands for, if you don't know, computed tomography. Big words, but CT does the job. Okay, computed tomography. Now, basically, what this means is, well, pixels and voxels are not in the syllabus, so if you see that, you can just breathe a sigh of relief. But a CT scan is very similar to an X-ray scan. It's actually a collection of X-rays. Okay, so CT scans are similar to X-rays, but instead of using a single detector, we have a range of detectors. We have an array of detectors, I think would be a better way to state this. So we have an array of detectors. We have many detectors, and the setup is basically something like this. We have an X-ray source, the same source of X-rays we used before, okay, maybe slightly more complicated. We have our patient. Don't question my drawing skills, just accept it. And we have our array of detectors. Okay, so I'll just make it seem like they're actually an array. And so this is the array of detectors. Our X-rays come from the source, pass through the patient, and then are received by the detectors, as they were for regular X-rays, two-dimensionally. And so what we get is a wider range of view, a greater depth, a greater resolution. But we can do one better. We can actually we can do this two ways. We can keep the detector and source stationary and rotate the patient, which would probably not be the most comfortable thing. And so the better thing to do would be to keep the patient fixed and rotate the source and detectors. So the source and detectors always directly opposite each other. They rotate around the patient, allowing us to take a full 360-degree view using X-rays. So what happens is the X-rays pass through the patient, and then we use, like the name suggests, high-power computers. And so what the high-power computer does is generate a 3D image. And so going from a sort of grainy black and white X-ray image, single X-ray two-dimensional image, we can get a 3D image or a 3D scan. And this is a lot better than a regular X-ray because it gives you much more information about the size, also the depth and or the location of any abnormalities, if there are any. And so CT scans are a lot better than X-rays, but should be avoided if not necessary, because a single X-ray is a lot of radiation to be exposed to. And you can imagine if you multiply this by so many more X-rays, I think there's a limit to the number of CT scans your doctor would allow you to take per year, okay, because the amount of radiation that you're exposed to is very high. And that's basically CT scanning. Place a patient at the center, rotate the source on the array of detectors, and get a three-dimensional image. Okay, so there's a lot more things to read there, which you should be doing. Open up the textbook, give it a read, but that's the basic concept behind CT scanning. Now, PET scanning, just because the word scanning is there, doesn't mean that it's the same. It's very different. Now, PET scanning uses a radioactive isotope. What does the word isotope mean? An isotope is any atom that has this different number of neutrons but the same number of protons. Okay, so the radioactive isotope that we use, well, we're going to discuss at least for PET scanning, is fluorine-18. Okay, we know you have the isotopes uranium-235, uranium-236, uranium-238, etc. Those all have the same number of protons, but they all have different numbers of neutrons. So they are all isotopes of the same atom, uranium. And so this is fluorine-18-9. This is highly radioactive. It becomes oxygen-18-8. And in that process, an electron is given off plus a neutrino. Neutrinos are, well, not massless, but they are tiny particles. Okay, and so basically what happens is when this decay occurs, a positron is released. Okay, this E0 is not an electron, but a positron. And so what this is an example of beta plus decay. So it's not an electron, it's a positron being released, which is the antiparticle, the anti-electron, the antiparticle to the electron. And so we can simply call E01, if you remember your particle physics and your radioactivity, that's a beta. Now, basically what's happening is this. I have a positron now that is produced in the body. So basically we provide a tracer into the body. What is a tracer? Remember from your notes, a chemical tracer is any isotope that is introduced into your body of some other element that's radioactive. So fluorine exists in your body. We can introduce a little bit more fluorine, but we can introduce the radioactive isotope of that fluorine, get it to move around your body, and let it decay when it reaches the place it needs to reach. Why? Why do we want something to radioactively decay in your body? Well, in your body, when the beta decay occurs, we have a very slow-moving positron. Now, positrons, like all antiparticles, are not common. Okay, so they're in the body, and positrons, not being common, will eventually find a partner electron. And they also have low momentum. They also move fairly slowly. They're in the body, they're slowed down. This process, which you probably would have remembered from, again, particle physics, quantum physics, is called annihilation. Annihilation occurs when a particle meets its antiparticle, they collide, they destroy each other or they annihilate each other, and a photon is produced. Okay, we'll just consider one photon for now being produced. And in this case, it happens to be that since beta decay is occurring, a gamma ray is usually produced. Okay, what do we do then? We then draw our detector in, because we need something to detect this gamma ray as it exits the body. So as the gamma ray exits the body, it's picked up again by an array of detectors, but this is an array of gamma ray detectors, and magic happens and we have an image. And the image actually has brighter colors for more gamma ray activity, or more yellowish colors for gamma ray activity, and more greenish, bluish colors, or reddish colors rather, for areas with low gamma ray activity. Okay, so basically there's a difference in colors, which if you saw images of PET scanning, you'll notice the colors are different. And so why is that important? Now, basically what that tells us, if we look at the different colors, we can tell the activity of a certain region. And if the activity is really high, it could be an indication that there's a tumor at that point. So when the fluorine gathers around a cancerous cell and the gamma rays are eventually produced, after the beta decay occurs and the electron and positron meet, the gamma rays will indicate that, hey, there's more activity here than there should be. And that can be picked up as an abnormality. And it gives us a nice two-dimensional, colorful image. Now, the mathematics of this is quite interesting. An electron meets its antiparticle, a positron, but what happens is two gamma rays are produced and not one. Now, why two gammas, you ask? Well, we said that these two particles have very, very negligible or zero initial momentum. Now, the conservation of momentum tells us that the final momentum of the two gamma ray photons must be zero as well. But what do we know? A single gamma cannot have zero momentum. A single gamma cannot have p equal to 0. And so two gammas must be produced. One will move to the right, the other will move to the left. They have the same momentum in opposite directions. Those momenta cancel because they are vectors. And so the final momentum can be 0. And so we get saved. That's why two gamma ray photons are produced in opposite directions. And so usually we place the array of detectors completely around the patient. And so we're more likely to get a three-dimensional image than a two-dimensional image. Now, the energy of these gamma rays, E, is also equal to the energy of the two particle and antiparticle, the mass of the electron times c squared. Right? Since we have one electron, one positron, both have the same mass. But that's also equal to 2 times the energy of each of the gamma ray photons produced, 2hf. So some simple mathematics gives us the frequency. If we wanted to find the frequency of the gamma rays produced, that's mc squared over h. If we put in the value of m for an electron, 9.11 times 10 to the minus 31, the value for c squared and the value for h, we get this frequency to be 1.24 times 10 to the power 20 hertz. Very, very high frequency, and that's why gamma rays are harmful. High frequency means high energy. But again, this is a last-ditch resort. I mean, we're not going to do this for every single patient, but we're going to do this if we really require the PET scan to be done. Okay, and now there's other things in PET to understand. From here, we can find the wavelength of the gamma rays lambda, but there's a lot for you to read. I've just covered the basics. For everything from ultrasound all the way to PET scanning, I've literally just covered the basics in this crash course just to help you maybe get started. If you're looking at it and it looks a bit daunting and overwhelming, it isn't. It's very application-based, it's not very mathematical, but it's very important nonetheless. So you can't be certain how many marks this topic will carry and how in-depth it'll be. But a little bit of reading will let you know that actually it's not that difficult of a topic. So maybe the next time we'll put up some problems and answers on this section so that the applications become a little clearer. So for me, for now, that's all. I'm Mr. K. This is Everything is Relative. See you next time.